Hello guys, welcome back to my channel. This is Homework 5 and MEB. Today we'll be talking about the Carnot cycle, the first and second law of thermodynamics, and Gibbs energy. So to start off today, I'm going to talk about the first law of thermodynamics, where it all begins. So the first law of thermodynamics basically is the law of conservation of energy, but with some added variables to incorporate heat flow. And I'm going to show you how that is. So first law, let's write it out first. So first law of thermodynamics. Thermo for dynamics, short. Alright, so the equation would be du equal to SQ minus PdV. Alright, so what is du? du is internal energy. D denotes U for the differential equation of U, which is internal energy. SQ is the sum of heat added to the system minus PdV. PdV is work. So to show you what that is, so we can just get work out of the way here, we can do dW equal to force times distance. Alright, which that is work. And then for thermodynamics, we do dW P times dA. So P is the pressure in the system. Alright, and then A is the cross-sectional area of the container. Okay? So now we have that. And so we're going to integrate this equation right here. So what we do is from 1 to 2. I'm going to take the integral from 1 to 2. So du equal to, so this becomes, the sum now just becomes Q. It just becomes the total added heat to the system. Alright? And then this becomes 1 to 2 PdV. So this becomes a change in internal energy, which is basically could be written as U2 minus U1 equal to the sum of enthalpy minus P external. Because now this is the external pressure. This is the external pressure being applied to the system, okay? The work being applied outside the system. V2 minus V1. So basically to summarize this equation, it would be Q minus P external change in V. So change external energy, heat added to the system, minus external pressure, times change in volume. Alright, and that is the first law of thermodynamics. Now there are multiple different, how can I say about this, different types of alternations that make it adiabatic, reversible, irreversible, and that will be discussed once I erase this board. As erased, I'm going to talk about the irreversible and reversible processes of an isothermal in the first law of thermodynamics. So, isothermal is when there is a constant temperature. So, basically T is equal to 0, constant temperature. And then this is a reversible part. This is a reversible part. It can be written as this. So, coming from our last, we came off with the first law of thermodynamics is equal to this, change in V basically, times the external pressure. Okay, so that's what we came off in an ideal gas law. Now we're going to talk about isothermal. That wasn't under an ideal gas law. This is an ideal gas law, and we're going to talk about that. So this is going to be this change in internal energy plus the added heat, and then we're going to have the interval of 1 to 2 again, rate constant times temperature divided by volume dV. Now rate constant is 8.314 joules times mole to -1 times the other one, Kelvin to -1, I'm pretty sure. Yep, alright, yeah, it's rate, okay, so that's the rate constant, it's equal to. And what we're going to do is from here is basically just simplify it a little bit. So it's Q minus the rate of times V2 divided by V1. And this is for an isothermal reversible reaction. Reversible. This is reversible. That's reversible. All right. Now let's do the irreversible isothermal with an ideal gas constant. Okay. So it's irreversible when it's under a constant pressure. Okay. There's external pressure on it, and it's under that. You just use this. Okay. So this is the change in U again, equal to the added heat in the system. The sum of the added heat in the system, do, minus the integral from 1 to 2, and then it's going to be the external pressure dV. And so I'm going to integrate this. It's going to be change in U equal to Q minus the external Q times V2 minus V1. Alright. Another form of writing this when it's under an ideal gas constant. Another form, or I guess, is CV dt equal to Q minus RT dV divided by B. Now CV is the heat capacity, and dt is just the derivative. Heat capacity. Okay, so this is an isothermal irreversible. Meaning you can't go back, which is basically a lot of things. And that's just because there's a constant external pressure. Alright. Here's the formula. And now I'm going to erase the board. Welcome back. Now the board is erased, we're going to start off with reversible and irreversible processes in the first law of thermodynamics. Okay, so we left off at the change in internal energy is equal to the sum of enthalpy minus PdV. This is the first law of thermodynamics. Okay, so what is isothermal? Isothermal is when the temperature is constant, okay? And this equation is preferably used in an ideal gas constant law. So we're just going to preferably ideal gas, okay? And it looks like this. So the change in internal energy is equal to the sum of the added heat minus the integral of the work, but the work in this case is RT, rate constant of the gas, which is 8.314 joules times mole divided by 1. Mole to the power of 1, and to -1 and Kelvin to -1. So I'm just divided by point dt. Alright? And then when we integrate this, we're going to get change in internal energy to this sum of the added heat, and then the RT, oops, excuse me, messed up there, RT times V2 minus V1. Oof, that is wrong. Hold on, 1 second, I messed up on this real quick. Alright, so here it is V2 over V1. This is the isothermal formula, meaning it's reversible, meaning it can go back to its initial states from the final to the end. It's like a tunnel, basically, just view, yeah? A cyclic tunnel, I guess. Now let's talk about a irreversible process in thermodynamics with the first law. And this part is also isothermal, but instead of a constant temperature, we're going to have a constant external pressure, in which I kind of alluded to in the first video, because it was the formula I wrote, but I didn't tell you what it was yet. Not the first video, earlier. Shit. Alright, so I kind of alluded to this in the first part of the chalkboard series, I guess, here. And I didn't tell you what it was, because we were just learning what the law was. So this is constant external pressure, which means equal to 0. So we're going to have the ideal gas again, so the rate constant is under the ideal gas, but instead of RT, instead of this, is going to be P xt dV, and then the interval from 1 to 2. So changing u equal to the cube minus the 1. Alright, minus P external, V2 minus V1. And we're just going to get changing u cube minus P external, the pressure externally, acting on it. It's the work being done on the system here. Change in V. Okay. Now we can write this as another reversible process I can write out is incorporating a new variable that I've not explained yet in this video, which is heat capacity. So let me write that out real quick. Hold on, let me fix this. Okay, first of all, thermodynamics. Now, here we go. This one relates to the first isothermal under constant temperature. Okay? So how I can write this one is Cv dt equal SQ minus the RTV dV. Alright. Now this is Cv is the heat capacity. Volume, this is the sum again, so it's just written as this. And then this would be written as, once we take the integral from 1 to 2, would be, let me just write this 1 to 2. And then down here we can write 2. Alright, there we go. Now we can talk about adiabatic processes. Adiabatic process means when the Q is constant. So this is gonna be a fun one. Lots of integrating. So what is an adiabatic process? It means there's no flow in the system. The flow has stopped. So imagine, I don't know, I guess container. No more heat coming in. No more heat going out. So this is written as this again, SQ minus, we can do PdV or I guess we can do RTB. Okay. And then we can do the DD again and the interval from 1 to 2. But Q is equal to 0. So what does this mean? So that means we have this. So just 0 minus 1 to 2. I'm just going to integrate that now. 1 to 2. So this would be, this is all messed up. Alright. That'd be the integrated form of that, but now we're going to have logarithmic. So which is ln. And then for our du, we're going to set that equal to the heat capacity of the system volume. So CV equal, I mean CV dt. And that's going to give us this. dV CV minus RT divided by B. Now we're going to have to integrate this now, which I just did already, so it's going to skip a little ahead here. When we integrate this and this, we're going to get equal to this. We gotta see that. ln V2. Now we're gonna have to solve for the so this part right here is ln T2 T1, and it is equal to RT ln V2 over V1, and this is at constant entropy because adiabatic, and it's basically an isocentric reversible process in thermodynamics. So constant isocentric, that's what it's called. And it is reversible. Okay, let me erase this. Back to the first law of thermodynamics up here. We're going to do an adiabatic with a constant pressure. Instead of like a reversible one, we're going to do an irreversible reaction. So what this is going to come out to be is, we're going to start out here actually. So ln V2 over V1 with the rate constant. How do you want to do this from here? ln V2, the rate constant, and then ln to V1 over V2 RCV, and this can be minus RCV. Well, it's going to be over, so 2, like that. Alright, so now we're going to have to figure this out to make it work. To do that, we're going to do this. So ln P2V2 over P1 V1 equal to minus R CV, which is then, gosh, I keep on doing that, sorry. CV, which then is ln over V2 V1, okay? So we want to get, obviously, the logarithmic stuff away from the equation. To do that, we're going to have to do this. Yeah, over, wait, P1, okay. And to do this, we're going to do V1, V2, R over CV, times V1 over V2. And now, Oof, let me erase some of this. Sorry. We're gonna go back up this way now. And it's gonna be P2, V2 because this goes over here. And this is gonna be P1, my bad guys. And it's gonna go over here. Which is equal to P1, V1. And then you're like, oh, where is the rate constant going? So basically, when you do this, this can become a plus 1. These two are going to cancel each other out. Make a 1, so be plus 1. So now it's going to be R over CD plus 1, R over CD plus 1. So remember, R is the rate constant, 8.314 joules, moles to -1, Kelvin to -1, and then CV is the heat capacity of the volume, and then P2 is the pressure to the system, and then P1 is the initial pressure, V1 is the second pressure, V1 is the initial volume, and then V2 is the second volume. So this is what happens when you have an adiabatic, irreversible process. This is irreversible under an ideal gas. Okay, let me erase this. So this is the Carnot cycle I'm going to be teaching you about now, and it basically kind of sums up irreversible and reversible reactions and processes from the first law of thermodynamics. So that's why I wanted to bring it up last for the first law. So the Carnot cycle is basically a theoretical idea for all engines. This is what makes all engines, I guess, theoretically work, or how they theoretically work. And so it's y-axis is pressure, x-axis is volume, and it's kind of hard to draw, but so it goes right here, A, B, C, D, and everything from the first law of thermodynamics is all these variables. But so it goes from, as I can do this, it goes A to B to C to D back to A. Okay? And then the internal energy is going to be equal to 0 from this. There's no, I guess, no internal energy in it, in the system, in this theoretical system we have here. And then the work is also going to be not a 0, but I'll show you. So this is going to be the sum of all the heat. You can write it as S, or just this Q, A, B, C, D, A. We'll cut that A. Then plus the work of A, B, C, D, A. Okay? Now, for deriving this equation, there's two different parts I'm going to have to go off of, and it's basically going to get a little messy here. So I'm trying to figure out where I want to put this on the chalkboard right now. Where should I start with? Okay, so I'm actually going to start with not deriving the equations, but explain them a little bit more using pictures. So we have a system here, the volume of A, and then you have the temperature of C here. And then we're going to call this an adiabatic compression. Alright? And then it's going to go from this system to another system. And then this system is going to be hotter. This system's going to be hotter than this system, okay? And now we're gonna go from cube. All right, we're gonna go to VC cube, volume of C to TH. That's just thermo. It's just temperature. Okay. And this is gonna be an isothermal expansion. All right. Isothermal expansion. Basically what that means is QH is greater than, the change in enthalpy is greater than 0. Now, there's one more part about this. It's called the adiabatic expansion. And so we're just gonna, I guess, from here to there, yeah, okay, as you can see. And then now there is no line in the system. I mean, like, there's no level, it's just the top part. What's completely full now, I guess. Stay completely full. Sorry. So it's gonna be V to D, and then T to C. And this is T to C. Wait, should it be? It should be VB. My bad. I messed up here. Okay, yes, this looks good. All right, so now this entire process, I guess we can call. So all of this, highlighted, I guess, is an isothermal compression. The temperature, well, it's going to be reversible, and it's compressing. So isothermal compression. Ta-da. Now I can start deriving the equations, but I just want to go over this one more time. So VA to TC is an adiabatic compression when it goes to B to TC. So A to B, B to C, C to D, C to A. Alright? And as you can see right here, VC to TC, B to C is when temperature rises. It's like, I don't want to say the exhaust, but it makes the car move, I guess. It's like a, I don't know, insert of energy, just say that. Insert energy here, so insert energy, not energy, but heat. I guess it's greater than 0, so, you know, it just goes faster, or something like that. And then A would be the exhaust, but since this is a theoretical system, it's the perfect engine, so there is no heat loss per se. It just works out better, I guess. I mean, obviously. So we're gonna do I'm gonna do the derivatives and the integrals, and we derive these equations right now in this process. I'm gonna erase this too, because it just gets in the way. Well, yeah, I can write it over here. That's terrible. I just messed this up, my bad. A, B, C, D, there we go, okay. So to start deriving this, we're gonna do changing U, A, B, C, D, A equal to Q, A, B, C, D. Oh. Yeah, let's just actually start from here. I'm not gonna rewrite all this because there's a lot to write here. So we're gonna start from here, and this is equal to 0. So this is 0 now. All right. So you go. Bring it over here. This will be QH. This is applying the ideal gas law of thermodynamics. I've been over in the video already. VC over VB, and then this will be T cold, which is when temperature is cold to rate constant times temperature, Ln, and VA over VD. Volume A over volume of D. Now, I guess, whoever figured out this Carnot cycle said these two are equal to each other. VA is equal to VD. I guess that kind of makes sense because VA is right here and VD is right there, and then VD is right here, and then VB is right there. So, you know, it could make sense, I guess. It's all theoretical here. And then, QH is equal to TH, which is then rate constant Ln over VD over VD over VB. And then we go from the QC to TH now. It's equal to negative R. Oh, so actually before I continue, let me explain something. The QH, QC, or whatever, that is the heat flow, like the heat path of which it's like the heat's flowing. It's like the direction it's going, I guess. So then we have RHTC, which is then QH divided by TH plus QC over TC equal to 0 because the internal energy is 0, or change in energy is 0. So there I have that part, and then this is only one fun part of the equation. And then I'm going to explain this part right here. The VC over VB equal to VA divided by VD. I'm going to explain that part on how that part is figured out. So how they do that is they start with the thermodynamics equation, change energy plus heat minus work, and they set Q equal to 0. So one way to show you how to do this, I'm just going to do and then apply ideal gas law of the equation. So it'd be VA over VB, and then du. Alright. Du, so change in internal energy plus heat minus work. Oh no, not this. Minus work dt. Okay. Oh, it's running in. Sorry. Minus e. Okay, so then we're going to change this to heat capacity. And then this is going to be equal to 0. It's going to be equal to 0. So this is going to become RT over V dV. And then from there, we're going to integrate it from A to B, okay? So A to B, A to B. Alright, and now this becomes this, the flow of heat to H, and the flow, the temperature H, which is entropy. No, entropy, my bad, I'm sorry. A little thick today, so can't really think that well. And VC is equal to VD, which is then equal to VB, and then you take the cross product of it, and you get VC over VB, and then VD over VA. So this is how we got that from the earlier on. I wish I could rewind, but we can't. So that's how we do this for the Carnot cycle. I'm going to erase this, and then I'll start explaining the second law of thermodynamics, entropy, and give straight energy. Alright, this is the second law of thermodynamics, and it is got some new variables basically here. So we have ds. Sorry about that. It is ds plus d surrounding greater than or equal to 0. Now ds is entropy, d denoting the differential of s, and then ds is the d denoting the differential of surrounding. So this also can be written as ds sum of q rev divided by t. Now, what is q rev and what is t in this fun little equation? T is equal to temperature. I just spelled temperature terribly wrong, but temperature. And then q rev is temperature, the heat in the system. The heat in the system, not the temperature. It's the heat in the system. Alright, so we can start. And q rev is also equal to du internal energy, d denoting the differential, and then plus pdv, so plus work. Okay? So that's what q rev is equal to. This is the heat in the system. So when we start deriving this equation, or writing it out basically, we can get TDS, the entropy inside the system, must be greater than or equal to the internal energy plus the work plus PdV. Okay? And then when we keep on deriving this equation out, we get du plus PdV. Then we get minus TDS greater than or equal to 0. That's not right, I'm sorry. Be less than or equal to 0. Okay. So, and T is temperature, but it's the absolute temperature of the system. So when I start writing this out more, we can get du. Alright, so we get du plus, Alright, so we're going to get du plus d of PdV, I think, no, PD, sorry, PV minus the entropy times the absolute temperature, which is less than or equal to 0, and then we just keep on basically writing this, we just keep on making it clear. Okay. And then look at this. So this part is equal to kind of leads into Gibbs energy. And what Gibbs energy is, it's right here. Gibbs energy is equal to H minus TS. So Gibbs energy of the system, or of anything really, Gibbs energy is equal to enthalpy minus absolute temperature times entropy, and that's Gibbs energy. So this is all that I have today for the video. I hope you enjoyed it. Make sure to like and subscribe. Thank you.